Look at the data your business generated today. Emails, server logs, customer interactions. It's a chaotic swirl of raw information. To make sense of it, traditional analytics forces that chaos into perfectly aligned, categorized grids. When applying machine learning to this information, you face a core choice. Do you train a system to predict a known outcome, or let it explore to discover hidden patterns? The first option is supervised learning. It is a highly predictable, goal-oriented approach, but requires your data to be neatly labeled. The second option is unsupervised learning. This path is exploratory, allowing the algorithm to operate on its own using raw, unlabeled information. The risk here is misalignment. If you apply a prediction-heavy model to an unclean dataset, you waste processing power on noise. If you use an exploratory model when you need a specific number, you'll find patterns that have no actual business value. We aren't going to debate which mathematical formula is technically superior. Instead, we're going to look at how to align these algorithms with your actual data budget and your target outcomes. Ultimately, this decision comes down to a practical trade-off: how much you are willing to spend upfront to prepare your data versus the level of certainty you need in your final prediction. The defining requirement of supervised learning is that it demands massive amounts of historically accurate training data, manually labeled by human experts. During the training phase, the algorithm makes a guess, checks it against the human-provided label, and adjusts itself to minimize the error. This diagram shows the complete supervised pipeline. The system maps the labeled data and their specific labels through the training mechanism, resulting in a perfectly categorized prediction. We use this approach for classification tasks, where the goal is to predict discrete categories, like filtering out spam emails or recognizing specific objects in an image. This graph illustrates classification in action. The model calculates a strict boundary that cleanly divides the known blue circles of Class A from the green triangles of Class B. The other major application is regression, which predicts continuous numerical values, like projecting future housing prices or forecasting stock market trends. This chart shows how regression establishes that forecast. The model identifies a trend, represented by the black linear line cutting through the dense field of red data points, to predict continuous outcomes based on past performance. But this precision comes with a steep penalty. The financial cost and human hours required to manually annotate thousands of data points are enormous. Furthermore, the model becomes rigidly biased by whatever the human experts tagged. You get a highly accurate, reliable prediction machine. But it is only a viable path if your project has the budget to fund that massive upfront data preparation. When dealing with vast, chaotic datasets that completely lack predefined outputs or target variables, we turn to unsupervised learning. Instead of following instructions, the algorithm analyzes the raw information and seeks to discover inherent structures and representations entirely on its own. This flowchart demonstrates the unsupervised pipeline. The input raw data box on the left moves directly through the algorithms, automatically sorting itself into separate output boxes without any external label inputs. The primary application here is clustering, which groups similar data points together to find hidden cohorts, like identifying entirely new customer segments based on purchasing habits. This plot shows how clustering identifies those natural groupings. Without any prior categorization, the model separates the angry, sad, and happy emoticons into distinct clusters across the axes, based purely on their similarities.
We also use unsupervised models for dimensionality reduction. This technique reduces the total number of features in a massive dataset while preserving the essential information for analysis. By completely eliminating the need for manual labeling, this approach saves thousands of human work hours up front. The trade-off is that the system creates categories autonomously, making the output opaque. You will need a human expert at the end to interpret if these newly formed clusters mean anything useful for your business. Unsupervised learning simply shifts the human labor burden. You save a tremendous amount of money on upfront data labeling, but you incur heavy back-end costs for expert interpretation. When deploying AI in heavily regulated industries like healthcare or finance, stakeholders require human-readable explanations for every decision the system makes, a concept known as explainable AI or XAI. Supervised learning inherently supports these explanations. Using techniques like feature importance, developers can point to the exact data point that triggered a specific decision. Unsupervised learning operates differently. Because it relies on discovering hidden patterns without target labels, achieving that level of explainability is significantly more difficult. This architecture diagram shows why unsupervised models are often considered a black box. The central bottleneck, or latent space, situated between the encoder and decoder, illustrates exactly where the unexplainable data compression occurs. When a model generates data samples based on these latent variables, it is incredibly difficult to interpret their meaning and influence without explicit target labels to verify them against. This creates a very severe compliance risk. Unsupervised models can easily perpetuate biases hidden deep within the raw data, biases that are nearly impossible to detect until the model behaves erratically in a live production environment. If your project requires a strict audit trail and transparent reasoning for its outputs, supervised learning is the only viable path, regardless of how much the data preparation costs. This comparison table breaks down the technical differences, particularly the stark contrast in input and output data requirements. Let's translate these traits into a practical framework for your next project. The decision starts with a vital question. What is your primary goal? Are you trying to predict a specific metric or explore data for unknown patterns? If you need to hit a precise target, you move down the prediction branch towards supervised learning. This path is for the optimizer. You have a specific outcome in mind, you possess the budget for extensive data labeling, and you demand high accuracy. If your goal is to discover structures you can't currently see, you move down the exploration branch toward unsupervised learning. This branch is for the explorer. You possess vast amounts of unlabeled data and want to uncover market anomalies without paying the prohibitive upfront costs of manual annotation. The cutting edge of the industry is already blurring the rigid line between these two paths through advanced hybrid approaches. Data teams now use cost-effective unsupervised models to pre-sort massive caches of raw data. They then feed those organized clusters into supervised tasks, maximizing accuracy while minimizing manual labeling costs. But to use these tools effectively, you have to look past the code and focus on the inputs. Success starts with clearly knowing whether you are paying for human labels up front or for expert interpretation at the end. Machine learning success is rarely about finding a mathematically perfect algorithm. It is entirely about aligning your chosen method with your data resources, your budget constraints, and your ultimate business objectives.